Welcome back. We're going to continue on looking at the different families of functions, their graphs, basic shapes, and parent functions. Next up are our square root functions. And all that means is that there is a variable under the square root symbol or the square root symbol. Now, square roots are inverse operations to squares. And so their graphs are going to look similar to one another. The parent function, the simplest, is f of x equals the square root of x. Or we can write that in exponential notation. F of x equals x to the 1/2 power. That 1/2 power indicates square roots. Now, the graph of a square root function, they increase quickly and then they flatten out to a very slow rate of change. So just a variable underneath that square root symbol indicates a square root function. Looking at the graph of a square root, it's going to start at the origin and we're going to have a slow rate of change off to the right. Once again, the parent function and the general shape of the graph. Now, square root functions, that's what we're on, are used in the power factor for electrical load distribution, the power versus the load, collision detection, direction versus size, and a fly ball from behind home plate. Kind of looks like a fly ball if you think of the batter here and how a fly ball acts going off to the outfield. Next up, we have exponential functions, and that is where a variable is found in the exponent of a function. And we use this, and you probably know some data that has been used by using exponential functions, and you've read about it in the news frequently. But they're usually in the form f of x equals some constant k to a power, where k is a constant. Graphs of exponential functions can grow, increase, or decrease at startling rates. They turn quickly from a gradual increase to a steep vertical rise. The parent function is f of x equals 2 to the x power, where our input values will become the exponents on our 2, our constant. All right, now the general shape, when we get a negative exponent, we have a very, very small number. And as we come in, it kind of creeps up and then it shoots once we hit those positive integers on a steep vertical rise. So the general shape of our exponential function. Exponential functions are used in savings accumulation on compound interest, interest versus time, the decay of radioactive elements, amount versus time, and look at that, I've listed it twice. So we're going to take one of those out, and the one I wanted to put in was the spread of rumors, the insiders versus the amount of time, and I will make that change on your note-taking guide before you watch this video. Rational functions are functions that are a ratio or fraction of polynomials. Meaning we've got variables in the numerator and the denominator. One polynomial is divided by the other. They're usually in the form of, and this is going to look familiar when we did our division, f of x equals g of x, some polynomial, divided by h of x, another polynomial. The graph of rational functions really vary depending on the complexity of those polynomials or functions in the numerator or top of the fraction and denominator. Parent function, simplest form, is f of x equals 1 over x, 1 divided by x. We have to have a variable in that denominator in order for it to classify and be categorized as a rational function. I'm going to do two sample graphs just because there is a lot of variation in the graphs of rational functions. So I'm going to first do our parent function, f of x equals 1 divided by x. And that graph has a shape like this. We've got two portions of that graph and it never goes to 0 because division by 0 is an undefined operation and we're not going to have a point there. The second one I wanted to show you is just a little bit different, and we're going to do f of x equals 1 over x squared. Now that changes the look of this graph. The right side is similar, but when we have that square in the denominator, it changes the location of the second half of that graph. And once again, notice I have variables in the denominators, making them rational functions. Now, we use rational functions, the lighthouse beam moving across a shoreline, the velocity versus the angle, the pressure of how about the pressure of a compressed gas, pressure versus distance, and repellent forces at close range can all be modeled with rational functions. Lastly, we're going to deal with logarithmic functions. When we're given an exponential function such as y equals some constant b to the x power, we can rewrite that as a log. And the log would be the log sub b of y equals x. Confusing. And we're not going to do logs this year. You'll be doing logs next year with Mrs. Menchaca. This is just meant to be an introduction to logs and the general shape. The parent function is f of x equals the log of x as a parent function. Now, their graphs of a log will turn from a steep increase, so it's going to go almost vertical on us, and then we're going to have a slow, gradual rise on that graph. The general shape of the graph is that steep vertical rise, almost straight up, and then gradual over to the right. Once again, I'm not graphing the real points here, just the general shape of that graph. Situations that are modeled with logarithmic functions, the Richter scale for earthquakes, the magnitude versus energy, measurements of sound, decibels versus intensity, and then I hate to tell you, cram for studying, the amount forgotten over time. You don't remember a lot. So that is our introduction to